Hello once again. We are now going to go through the review for the test that we're going to run for next week. I want to make sure you guys are really ready for this thing. So I posted up the review for you guys, and now I'm gonna go through the solutions to that review so you can make sure that you have the correct answers. And if you didn't have the correct answers, you are aware of how to work the problem. Again, if you have questions, feel free to put them down below or send me a message, and I'll get to those as quick as I can. But let's go ahead and get into this so we can see how the test is going to run. I guess before I get to any more, I do want to say that the test that we're going to have in class is going to, I'm going to give you basically a PDF of the problems. Y'all are going to work out the answers. If you want to print it off and try to work them all on the test, that is perfectly fine with me. In fact, probably be a lot easier for you to work and grade, or me to grade. If you don't have a printer, don't have access to a printer, that's fine. Feel free to work them on just regular sheets of paper. This is going to be a little bit more difficult because there's some polar graphing in there. Just take a picture of your answers, no matter which way you do it, or scan them in and get them to me that way. If anybody has any issues that they need to kind of send to me, do those soon so that I can make sure that we're prepared to make sure that you have all the ability you need to be able to get in your answers. Okay, so let's go into this thing. Let's look at one of the first types of things you're going to be asked to do on this test, and that is I'm going to give you some polar points, and you're going to be trying to find out equivalent polar points because, like we discovered when we were going through the lesson, if you go back through into 9.1, you'll see that we saw that polar points are not unique. A point in the Cartesian coordinate plane, an x and a y, is a unique coordinate point. So like 3, 4, that's the only way to write that particular coordinate in rectangular. Um, but if I want to write something in polar, there are an infinite number of ways to write it. So we're going to go through some ways to do that. I'm going to do this one in degrees and one in radians, so you kind of have a little bit of practice with both. So for example, for A, we have the point 560, so I'm not counting this as one of my three ones that are equivalent to it. I'm going to try to find three additional ones that are equivalent. So one thing I could do is I could add 360 degrees to this, and so I could end up with the point 360 plus that is 420. So that is an equivalent point. Another thing I could do is I could add instead 180 degrees. If I add 180 degrees, that goes to the opposite side of, if I'm at 60 degrees and 5 out, if I go to 180 degrees from here, I'm over there, if I go to the negative radius, I'll end back where it was. So if I say negative 5, add 180 to this, 240, this 240 degrees, then going back 5 spaces, going the opposite direction in 5 spaces, is the same thing as saying 560. And we can do the same thing by either subtracting 180 and putting a negative on it, or by subtracting 360 and leaving the first number alone. So I can also say 5 negative 300 degrees. Okay, so that gives you kind of an idea of what to do. Um, you can do similar things when it's in radians, only instead of 360 and 180, we're going to be talking about pi and 2 pi, right? So if I add 2 pi to this, I would end up with 2 comma 3 pi plus 3 pi over 4 plus 8 pi over 4, which is 11 pi over 4. That's one way to do it. I could add pi to this and make it negative. So add 4 pi over 4 is negative 2 and 7 pi over 4. Or again, I could subtract 2 pi. So I could get 2 and negative 5 pi over 4. So again, like these are the ways that we can do this. Not too crazy. You do need to be able to know how to recognize or find points that are equivalent to another point. All right, now let's talk about finding polar distance. So just a reminder, Again, in the first section, we talked about the polar distance formula that was derived from the law of cosines. That formula is that you take the radius of the first thing, square it, take the radius of the second thing and square it, and subtract it times the two radiuses multiplied together times the cosine of the angle between these 2 points. So to figure this out, this particular one out, I'm going to be taking the square root of the first radius squared, so 36, plus the second radius squared, which is 9, minus 2 times 6 times 3 times the cosine of the angles between these 2 points, 5 pi thirds minus pi thirds. This gives me the square root of 45 minus 36 cosine of 4 pi over 3. So now I need to find out the cosine of 4 pi over 3. Cosine at pi thirds is a half, so at 4 pi thirds, since that's in the third quadrant, it's going to be negative 1/2. So the square root of 45 plus 36 times a half, because I'll multiply the negative out, or the square root of 45 plus 18, which is the square root of 63. The square root of 63 is almost 8, not quite 8. I would be fine with you leaving it as a square root of 63. But if you were curious and you wanted to write it out, I would prefer you give it to me in a way that is going to be what you'll do next year in AP Calculus, and that is give me 3 decimal places of accuracy, so 7.937. Okay, now let's talk about simple graphing. So I both want to be able to graph points in polar, and I also want to be able to graph the very, very, very simple polar equations. So pi fourths, which I don't have a line for, but I know pi fourths lies in between pi thirds and pi sixths. I want to go -2. That means I'm going the opposite direction, 2 spaces. So where is that point? It is right here. 3 and -5 pi sixths. So I go -5 pi sixths, which takes me to 7 pi sixths. Go out 3, 1, 2, 3, and we're right here. Simple equations. Graphing theta equals 4 pi thirds. Here is 4 pi thirds. Theta equaling that, where all the radius values, where the angle is 4 pi thirds, including the negative radius values. So remember, a theta equals is a line that passes through the origin. Radius equaling -2. Well, let's see. If I'm at 0, radius equals -2 over here. And if I'm at pi sixths, radius equals -2 is here. And if I'm at pi thirds, it'd be there. And pi halves would be here. And you can kind of see it's at all the places a distance of 2 away from the origin. It ends up being a circle of radius 2. Alright, so that gets through simple graphing. Now let's move on. Let's talk about identifying a polar curve by seeing its equation. So when you see these equations, I want you to be able to recognize which type of classic polar curve this is. I gave you a list of these in 6.2, section 6.2. A whole list of them: limasones, lemniscates, circles, polar roses, the spiral of Archimedes. I just want you to be able to identify them. This very first one, when it is a cosine theta or b or an a sine theta, that is a circle. So it's a circle here. B, this is an a plus b sine theta or an a plus b cosine theta. That is a limason. This one is also an a plus b sine or cosine theta, but the a and the b happen to be the same. This one's in fact a cardioid. It is a type of limason. But more specifically, it is a cardioid. I would expect you to know the difference between a cardioid and a lemma that is not a cardioid. Okay, I do expect that level of detail. This particular one, an A sine B theta or an A cosine B theta, is a polar rose. An r squared is equal to something of a 2 theta, so r squared equaling a squared cosine of 2 theta or sine of 2 theta is a lemniscate. And lastly, when you have r equaling a theta plus b, it is a spiral of Archimedes. All right, so we can identify things. Can we convert from polar to rectangular and rectangular to polar? I hope so. So let's go through this one. I've got this polar thing, -2, 5 pi fourths. I'd like to convert it from polar to rectangular. So I need to know my formulas. X is equal to r cosine theta. Y is equal to r sine theta. So in this case, I have -2 cosine of 5 pi fourths, and I have -2 sine of 5 pi fourths. Cosine of 5 pi fourths is -√2 over 2. So we end up with √2. Sine of 5 pi fourths is also -√2 over 2. So it's also square root 2. So I get the point √2, √2. B. Convert it from polar to rectangular, rectangular to polar. I'm given the point -1, 1. Well, I know that r is equal to the square root of x squared plus y squared. And I know that theta is equal to the inverse tangent of the y over the x. But when my x is negative, I need to add pi to the answer. So this is the square root of 1 plus 1 when you square both -1 and 1. So the square root of 2. And this is the inverse tangent of 1 plus pi. The inverse tangent of 1 is pi fourths. Excuse me, it's not positive 1, it'd be -1. So it would be negative pi fourths. I want to add pi to this, and I'll end up with 3 pi fourths. So in polar, my r is √2, my theta is 3 pi over 4. Okay, I'm going to ask you to graph something, and I want you to make sure that you understand something. I copied exactly the wording I used on your test. The table must be completed, and all points must be represented in your graph to get full credit. So when you're going through this and you're working it out, I expect to see all of these points. Okay, so that's all 13 points graphed somewhere. Really, I guess it'd be 12 distinct points. So first thing I got to do is put in the things. So if I put in 0, I get 3 plus 1, which is 4. When I put in pi sixth, I get 3 plus √3 over 2, which we're going to work out as a decimal equivalent. So it's 3 plus the square root of 3 divided by 2. And you get 3.866. When we're going to pi thirds, we have 3 plus 1/2. Pi halves, 3 plus 0. At 2 pi thirds, we're going to be at 3 minus 1/2. At 5 pi sixths, we're going to be 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 is 3 minus √3 over 2. So again, I'd get a decimal equivalent. 3 minus √3 over 2 and get 2.133. Pi, we're going to get 3 minus 1, so 2. 7 pi 6, we'll get 3 minus root 3 over 2 again, so that's that 2.133 value again. Then again, we'll start seeing these kind of repeat themselves, 2.5, 3, 3.5, the 3.866 value, and back to 4. So now that you've gotten all your points, now I expect you to start plotting these things. I do not want to see some sort of rough estimation of what it looks like in your graphing window or at some graphing utility you pulled up online. I want to see the table of values, and I want to see each individual point listed on the actual polar graph itself. Okay, so don't try to shortcut your way through this problem, please, or you will lose credit. There's 4, there's 3.86, there's 3.5, then we're down to 3, then we're down to 2.5, then we're down to 2.1, then we're down to 2, back up to 2.1, back up to 2.5, back up to 3, 3.5, at 3.866, and then back to 4. So this thing is, hopefully you remember from the last problem we worked. Oh man, that is not a good drawing on a computer, but you'll just have to excuse that squiggle right there. This is a lemmason. It is not a circle. Okay, I saw a lot of things on the worksheet when people were drawing them out where there were parts that should have been more dimpled in that looked a lot like circles. I'm not going to be over analyzing your graph, but it should have the points properly graphed at the right spot. If I see that you graphed the points in the right spot and you followed them in the correct order, then I'm going to be inclined to give you the credit. If I don't see the points listed in the table, I don't see the points on the graph, and or you don't follow them in the right order, I will not be inclined to give you credit. All right, moving forward. Converting the equation from polar to rectangular. So here's an equation in polar. So I need to convert it to rectangular things. So remember, x is r cosine theta, y is r sine theta. I don't see any of that quite right there, but I do see this r on the outside of the parentheses that we can multiply in. So I have 2r cosine theta when I do that, plus 3r sine theta. Oh, that's really convenient for me. Now I have an r cosine theta, which is x, and r sine theta, which is y. So I have 2x plus 3y is equal to 4. So that equation right there is actually a line. All right, I have y is equal to x squared. I'd like to convert that into polar. So my y becomes r sine theta. My x becomes r cosine theta. That's going to be all squared. So I have r sine theta is equal to r squared cosine theta. And at this point, I would bring everything to one side. R squared cosine theta minus r sine theta is equal to 0. Factor out an r. And we have basically two things. We can have an r of equal to 0, and we can have r cosine theta minus sine theta equal to 0. Solve that one for r, and you get r cosine theta is equal to sine theta, or r is equal to sine theta over cosine theta, which is tangent. So to get this particular one, you can just have the r is equal to tangent of theta, and you are good to go. All right, next one. Complex numbers. So this is one of the last sets of things we did. This was in section 5. Well, actually, I guess it was in section 4, the one we did before we did the last section on Argand diagrams, or on DeMoivre's formula. So we have some complex numbers I've given you here. I'd like to do some simple calculations. So we're going to take 3 times z1, z2, plus z3. That gives me negative 12 minus 15i plus 7 plus I, or negative 5 minus 14i. So that's A. B is multiplying them together. So let's do that in a different color. Z1 and Z3. So 3 minus 6i times 7 plus I. When I multiply these together, I have to use the distributive property. That is 21 plus 3i minus 42i minus 6i squared. Remember, the I squared turns into a negative 1, so that'll become plus 6. And then we can add together our like terms and get 27 minus 39i. Division, I'm going to take 7 plus I, I'm going to divide it by 3 minus 6i. To do the division and be able to write it in our standard form of a plus bi, we have to multiply the top and the bottom by our conjugate. The conjugate of the denominator. The denominator is 3 minus 6i, so I have to multiply top and bottom by 3 plus 6i. When I multiply out the numerator, that gives me 21 plus 42i plus 3i plus 6i squared. And when I do the denominator all out, that is a plus b times a minus b. So that's going to be a squared minus b squared, or 9 minus 36i squared. We already talked about what happens with the I squareds. They turn into negative 1s. So I'll have 21 plus 45i minus 6 in the numerator, and I have 45 in the denominator. Or what I'll have is 15 plus 45i all divided by 45. To break that apart, and so it's a plus bi, I break this into two separate fractions. We get 15 over 45, which is a third, plus 45 over 45, which is just going to leave me with the I. All right, so we have finished that problem. Last set of problems here. This was dealing with polar complex numbers that are in polar form, how to multiply, divide, and use DeMoivre's formula. So we're going to multiply these things. Remember, it was a lot easier to do them when they were in polar form. We didn't have to do this big distributive property and worry about changing I squareds into negative 1s. We could just multiply together the radius values. So 2 times our 5 is 10. And then since they're being multiplied, we get to add together the angles. So I'll have 3 pi fourths plus 7 pi 6. So I got to get those in like denominators. So that is going to be 9 pi twelfths plus 14 pi twelfths. When I add those together, I get 23 pi twelfths. So I'll have cosine of 23 pi twelfths plus I sine of 23 pi twelfths. So ignore that part for this one, that last little part about writing it in a plus bi, unless you have your calculator handy, and then of course you could go ahead and write it out. On the test, they're going to be ones that work out nicely to things on the unit circle. So if you don't have a calculator handy, that can handle that you'll still be fine. All right, last one. We're going to be subtracting these two things because they're being divided. The 2 and the 5 will divide and get 2/5. And this time, instead of adding the angles, we will subtract the angles. So again, we'll have 9 pi twelfths. This time minus 14 pi twelfths. And get negative 5 pi twelfths. So again, it'll be cosine of negative 5 pi twelfths plus I sine of negative 5 pi twelfths. And again, the same rule goes as the one before. I don't expect you to work that out in your head, a calculator use is fine. So if you have a long decimal answer, that would be okay. I know we learned how to get the ones that were the 12ths when we did our trig chapter, but I don't want you to have to go through half angle or angle addition subtraction formulas to be able to get to the answer here. I just want to make sure you know how to do the operation of adding or multiplying and dividing complex numbers in polar form. Okay, last we have DeMoivre's formula. We're going to try to use that to get this 1 minus I to the 6th power. But doing that by hand, if we were going to multiply this all out, we're going to have this all raised to the 6th power. We'd have to use like the binomial theorem or Pascal's triangle or something. It would be a big, huge mess. But luckily, DeMoivre came along and he had something a little simpler for us. He's like, if we can put this thing in polar form, we can kind of use an extension of what we did for the multiplication to raise things to a power. So the first thing I need to do is get this thing into polar form. And so to do that, we remember our r is the square root of our a squared plus our b squared, so the square root of 2. Our theta is the inverse tangent of our b over our a, so negative 1 over 1, so negative pi fourths. And so what we're going to end up with here is to raise this thing to the 6th power is we're going to say we're going to take root 2 and we're going to raise it to the 6th power, and we're going to multiply that by the cosine of 6 times negative pi fourths plus I times the sine of 6 times negative pi fourths. Basically, the power goes to those 3 locations. Root 2 to the 6th power is 2 cubed. It's basically 6 divided by 2, so 2 cubed. So this is 8. So we end up with 8 cosine of negative 6 pi fourths, or negative 3 pi halves, plus I sine of negative 3 pi halves. To write this in standard form isn't going to be that difficult. See, because I know that the cosine of negative 3 pi halves is 0, and the sine of negative 3 pi halves is 1. So what I really end up having is 8 times 0 plus I, or 8I is my final answer. Alright guys, that's gone through all the problems, so we've seen them all now. Again, if you have questions about this, something I didn't explain fully, feel free to comment or send me a message, and I'll be happy to try to get back with you and answer this the best I can. Alright guys, take it easy, and I'll see you soon.